Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so thank you very much. Thank you very much for the invitation. It's a great honour to be invited to give this tutorial. I'm sure the organisers could have found someone much more kind of prestigious to give this. As reminded, this is blatantly clear in the Judea Pearl talk this morning, where the introducer read out a list of accolades as long as his arm. The speaker was talking about a field he invented, and all the primary kind of innovations in. And that's not what I'm going to be doing today at all. This is I did my PhD, I finished it in 2008, and I was probably the first person to do my PhD on ABC. I'd got into it very early on, but I'm going to enjoy telling you about it today. Okay. So, as Dan said, I'm not a machine learning person, I'm a statistician. I'm not really sure what the difference is, but I thought I'd take a little bit of time to say about the type of problems that ABC tends to get used in. Okay, so the power's not working down here. Okay, so the key area that ABC is looking to try and address is how do we make inferences about the world from a simulation of it. So nowadays, most scientists build computer models, and rather than experimenting on the real system, they experiment on their computer simulator. Okay? So this is particularly important in climate science, for example, where we're potentially talking about reorganizing the world economy on the basis of predictions from a complex computer model. So it's very important we're able to do statistics and analyze these models properly. So the type of questions that we are interested in is how do we relate simulators to reality? Okay. We know that simulators are imperfect representations, they're just models. So in order to learn anything about reality from the simulators, we have to relate them to reality and to the data in some way. How do we estimate tunable parameters? So the calibration problem. So we think about these simulators like airplane cockpits, dashboards. Okay? There's lots of levers, knobs, and things we can twiddle and twirl to try and get better behavior from our simulator. And if we have the wrong setting, we'll get incorrect predictions or poor predictions. So we've got to find the right setting. How do we find parameters that give us good predictions? The question is, how do we deal with computational constraints? Okay? We have finite computer power. Simulators can be very complex and take months to run or seconds to run. Either way, we have something to overcome and deal with. And finally, how do we make uncertainty statements about the world? So computer simulators typically, they're not inherently random. We have to supply the randomness ourselves. Okay? If you run the simulator with the same seed time and time again, we'll get the same answer. Whereas if we do a physical experiment, time and time again, we'll get different answers. And it's that uncertainty in the physical experiment that allows us to do statistics, the classical statistics. So computer experiments has needed a new set of methodology to try and answer some of these questions. Okay. So we're going to focus particularly on the calibration problem, but all these aspects are going to come in. So a bit of notation. So for simulators, we're going to think about specifying parameters, theta, and initial conditions. And the simulator, which I'm going to call f of theta, then generates output x. We're going to be interested in the inverse problem, if you like, or the calibration problem. So given some data, d, that we observe, we want to estimate what parameter values, theta, explain this data. Okay, so we've got theta, the inputs, f is our simulator, generates output x. We're going to say what theta led to this data d. Okay. Now, for Bayesians, this is very simple. This is a question of finding the posterior distribution. So, again, basic notation. The posterior here is pi of theta given d, the posterior, the parameter given the data, and that's proportional to the prior times the likelihood. The likelihood is the probability of the data given the parameter theta. So this is a picture from a problem I like working on. It's from evolutionary biology, and it's typical of the kind of problems that ABC methods are used on. Okay? So the problem is, when did the primates evolve, essentially? When did it diverge from other mammalian species? So the data we have are DNA from extant primates. Right? So we can go into the jungles and bag a monkey and take a bit of blood. We also have fossils. So we have a pattern of fossils that could be dated to the last 55 million years. And we want to say, given this data, given this pattern of fossils, what can we learn about this inferred age, this divergence time down here? Can you hear me if I walk away from the podium? Yeah. So very simply, we have a model of evolution. That's a forwards model. It generates sample fossil data sets. And we want to say which of those match up with the ones we have. And it's very difficult to solve this problem in any way other than using methods like ABC, which I'll tell you what it is in a moment. Okay, so the beautiful thing about being a Bayesian is that philosophically it's incredibly simple. We do the same thing in every problem. We have a model for our data, given some parameters theta, and we're just always finding the posterior, pi r theta given d, and that's always what we do in every problem. So philosophically it's very simple, then the difficulty comes in with computation. So the normal difficulty in Bayesian computation is what I call the usual intractability here is not knowing this normalizing constant, the thing in the denominator here, pi of d, the probability of the data, when we've integrated out the parameters. Okay? And this is what methods like MCMC were invented for, to help find the posterior when we can't do this calculation by hand. Well, we've got some class of problems that are harder than this. Okay? So Ian Murray and Zubin Garamani and David Mackay introduced this class of doubly intractable problems and gave a methodology for solving them. So they said a problem is doubly intractable if the likelihood function, the probability of the data d, given our parameter theta, is only known up to a constant of proportionality, where that constant depends on some parameter theta and the constant's unknown. So they said this was a doubly intractable problem. And they were able to write down an MCMC algorithm where they basically introduce some auxiliary variables and showed us how to solve these type of problems. ABC is for the harder class of problems again. It's for what I've called completely intractable problems. So I said that a problem is completely intractable if pi d given theta is unknown and can't be evaluated, okay, even up to a normalizing constant. So ABC, approximate Bayesian computation, are for when all we can do is simulate from the simulator. We know nothing about the form of the likelihood function itself, the density of the data given the observations. Okay. So this type of problem occurs time and time again, these completely intractable problems. In particular, a particular class of model for which they appear all the time is when we have a branching process that underlies our data generating process. So in genetics, epidemiology, ecology, these types of structures are common. So we have a branching process that describes something that's going on underneath the data. So maybe it's evolution in my evolutionary biology example, or mutation of cells, or whatever. And then we sample this discretely. And there are lots of things about the branching process we don't know. So for example, if you want to know the number of branches in any given time window, we don't know how to calculate that distribution. Okay? It's intractable. But we can simulate it. We can simulate branching processes very simply. And so we resort to these simulation methods. Okay. Okay, so given a complex simulator for which we can't calculate the likelihood function, how do we do inference? So I'm going to tell you today about a particular way called ABC, or Approximate Bayesian Computation. Now, I tend to prefer to call the method ABC rather than Approximate Bayesian Computation because there's lots of different Approximate Bayesian computation routines which this community knows lots about. Okay? ABC refers to a particular subset of them, the ones that we're going to use simulation rather than likelihood calculation. So I'm going to call it ABC, and I think that's a better name because it's clear what we mean than Approximate Bayesian Computation. Okay? And the main idea is that they don't require explicit knowledge of the likelihood function. We don't need to know anything about the likelihood, but we do need to be able to simulate from the model cheaply. So we're going to do all inference using simulation only. So we just need to be able to, given a parameter value theta, cheaply simulate sample data sets from the simulator using that theta. Okay. They're also called sometimes likelihood-free methods. I don't like this term much either because, as Neil Lawrence keeps pointing out to me, they're not likelihood-free at all. There is a likelihood function under there. We just don't know what it is, and we can't calculate it. Okay? So they're not likelihood-free. We just don't need to use the likelihood function in order to make progress with them. Okay. And if you I mean, just a quick show of hands. How many people have come across ABC algorithms before? Okay, so not many. That's good. Okay. It gives me something to tell you about. So they become very popular in the biological sciences. Okay, so if you work in genetics, epidemiology, they're becoming quickly the first port of call for modelers who have complex models but might not necessarily be expert statisticians and be familiar with advanced Monte Carlo things. It looks like this popularity is going to keep growing. Okay? So over the past 10 years, the number of papers has skyrocketed. The reason I think they're popular is, firstly, they're simple, they're almost trivial to implement. Okay? You don't need to know much. If you're numerous enough to build a stochastic model, you're numerous enough to implement ABC, basically. So they're very popular in biological communities for that reason. They're kind of intuitively obvious as well. If you didn't know what you were doing and you wanted to make up an algorithm for calibrating simulators, the basic ABC algorithm is almost what you'd think of to do straight off. Okay? They're very intuitive. They're also embarrassingly parallelizable, so there's lots of GPU computation and big clusters being used, and we can kind of brute force do inference in these models. The final thing is they can nearly always be applied. If your model is cheap, or you have enough computing power, there's always an ABC algorithm you can write down, pretty much. So the other thing to note is that they can, at least upon first viewing, seem very crude. But they have an important role to play for these reasons. And I think it's interesting for that reason to study them and to think about how we can improve them in some way. What can we do to make them better and understand what they are doing? So if you think about what the first ABC paper is, it's not very clear. Okay? So the first paper to use the term approximate Bayesian computation in this sense was a paper by Mark Beaumont, Zhang, and David Balding. There might have been a fourth order, but Beaumont and Balding were definitely first and last authors. In 2002, they used the term ABC, but they were building on work by Simon Tavray from 1997, Tavray and Donnelly, and Pritchard and others in 1999. So that's what we thought for a while with the first papers, but as with all these things, it's such a simple idea. If you look hard enough, it turns out the ideas have been proposed many times in different communities. Okay. So Diggle and Grattan, a red paper for the RSS, the Royal Statistical Society in 1984, or Don Rubin in 1984 had a very similar kind of ideas. Okay. And in most user communities, in hydrology and biology, there are similar algorithms that are built up that are used. Okay, so I'm going to fulfill the brief today and treat this as a tutorial rather than a research seminar. So the material is largely review material, although there will be some more advanced things. So I apologise if anyone's very familiar with ABC. You've probably heard most of this before. There are some newer bits. Okay. But this is the basic structure. I thought go through the basic algorithms, talk about the efficient developments that have come out recently, in the past 10 years, and then links to other algorithms. I mentioned the different communities have very similar algorithms, and it's informative to think about these links. Then we'll have a break, 5 minutes or so to give people a chance, stretch their legs, and then we'll do the second part, which is a more modelling and machine learning type of approaches. Okay. So these all involve models of some sort. This part is very much Monte Carlo, this part is more modelling and dimension reduction. Okay, so the basic ABC algorithm is very simple. Okay. To simulate, remember what we're trying to do? We're trying to get draws from the posterior of theta given the data. Think about the rejection algorithm, which you all know about from any Monte Carlo class you've taken. If we pick theta from the prior distribution, if we then accept theta with probability proportional to the likelihood. Okay. This gives us draws, samples from the posterior distribution of theta data. Okay. Now we can't do this because we don't know this likelihood. So there's a kind of a mechanical version of this algorithm that, as I say, kind of the thing you might imagine you'd do if you knew no better. So pick a theta from the prior, simulate some data, x, from the simulator using theta, and then we're going to accept theta if the simulated data x exactly matches the real data d. Okay. So this, it turns out, is exactly the same as this algorithm. It's just kind of got this mechanical bit. So it's like a mechanical version. We can turn a handle and generate output doing this. A point to note for later, the acceptance rate here is the marginal probability of the data. So what we get if we integrate out the likelihood. So you can see that if the probability of the data is small, or if D is continuous, okay, we're never going to get any matches here. Okay? If the probability of observing D is tiny, or if X is continuous, this is never going to happen. So we can change this exact algorithm to our first ABC algorithm, which is a rejection algorithm, and I've called it the uniform rejection algorithm for reasons that become clearer later. And it's the following. Pick theta from the prior, simulate X from the model, and now we're going to accept theta if the distance between the data and X is less than epsilon. So in other words, if we're close, if the distance between X and D is small. Rho is just some distance measure here, and epsilon is just some tolerance that we set. Okay. So the key way to understand this algorithm is if we let epsilon get very large here, we let epsilon go to infinity, we're going to always accept. We're going to accept every value of theta proposed. So what we get back is the prior. Okay, there's no rejection, so we just get the prior distribution back. If epsilon's 0 here, and if rho is a metric, then we get this algorithm, and so we get the exact posterior. So epsilon controls the accuracy. Epsilon large, we get very inaccurate results. Epsilon small, we get accurate results. But it also controls the computability, how much computation we have to do in order to get an answer here. If epsilon's small, we're only going to accept rarely. We're going to have to simulate for a long time to get a large enough sample. If epsilon's large, we're going to not have to do very much work at all. Okay, so epsilon kind of reflects this tension between computability and accuracy. Okay, so a visual demonstration to kind of show you everything you need to know about ABC. So I've just made up some very simple models to create some simple pictures. It doesn't matter what the model is. Okay? There's some model for X, given the parameter theta. And all we're going to do, we're going to look at whether, and I've supposed I've got some data that is D is 2, yeah? And we're going to look at doing ABC here. So along the x-axis, we've got theta. You can hear me over here. Not very well. Can you turn this mic off? Is that possible? I'll stand back over here.
You could use this one.
No, I'll just stand over here, it's fine. So along the x-axis, we've got theta here. Along the y-axis, we've got the data, the x, simulated from the model. So I've just done a bunch of simulations, pick a theta, pick an x, and we've just... Thank you. I think I got worried for a minute. So I've just cut off the left and right hand end, just to the interesting bit. So the data here is represented by this red line across the middle, this is D is 2, and ABC just says, if we get close enough to the data, accept. Okay? So epsilon plus or minus epsilon on either side here. And you see all the red points are the ones we're going to keep, put to one side, and they're going to go into our posterior sample. So over here we've got the histogram. The red line is the histogram from all these red points. Okay? And the black line is just the truth. If I did MCMC on this model, this is what I'd get. Okay? So you can see we've got a posterior here, the red line. This is the ABC approximation to this trimodal thing. So with epsilon equal to 10 here, we've got a fairly, well, we've got a decent approximation that we've ruled out anything less than 3 or bigger than 3, but we don't know much in between. We know nothing. Okay. To make epsilon a bit smaller, we're saying we have to get a bit closer to the data. We start to cut out this lower trough down here, and we start to learn a bit. Cut a bit more out, we start to learn a bit more. We've learned there's no chance that theta's 1, and so on. Until we get down to quite a small value of epsilon. And what we're getting now is a pretty good approximation. We've learnt all 3 modes. We're not quite getting the height right. But we're requiring that we get simulations that are pretty close to the observation D. And that's giving us a pretty good approximation. So you can think about the exact posterior here would be what we get if we do with a slice along the red line and we didn't have to do the sampling. Okay? So if we just took a slice through the likelihood surface along here, we'd get the black line. ABC taking a slightly wider slice, so we're getting a slightly more dispersed posterior. Okay, and that's basically it. That's the main idea behind ABC. Okay, there's lots of problems with doing ABC. The first one is that if the data are too high-dimensional, we might never observe simulations that are close to the field data. So this is kind of the curse of dimensionality, right? Space gets very large in high dimensions, so if we've got a 100-dimensional X or D, data is 100-dimensional, so not very big, then there are, 2 to the 100 corners in our, I'm talking about theta here. Space gets big quickly, is basically what I'm saying. Okay? If we're in a higher dimension, it gets harder to find observations that are close to the observation. So what we do instead, we use a summary statistic and project the data and the simulated output onto a lower dimensional space. So with our summary, S of D, we now just accept theta if the difference between the summary of the observation, S of D, is close to the summary of the computer output. Now, if S is a sufficient statistic here, this turns out to be equivalent to the previous algorithm. But in practice, of course, we never know sufficient statistics. So what I'll talk about later is how do we find good choices for S. But for the time being, I'm just going to ignore this approach and just assume that we're doing ABC without summaries. Okay? Everything I'm about to say, you could pretend I've got S's in if you wanted, but we'll come to how we choose S later. Okay. So one of the questions that we want to know whenever we're doing these inference algorithms, approximate inference algorithms, is what does the error look like? What are we really doing here? And I think there are two ways we can think about algorithms. Okay? We can think about them algorithmically or probabilistically. What's the probability model that corresponds to the algorithm we're using? So for example, in linear regression, algorithmically we're just finding a straight line that minimizes the sum of squared errors. Or probabilistically, we've got a linear model with Gaussian errors and we're fitting it using maximum likelihood estimation. Well, the Kalman filter was originally proposed by Kalman as linear quadratic estimation, and we're finding the best guess at a trajectory that minimizes some quadratic penalty function. Now we tend to view it as a Bayesian filtering solution to a linear Gaussian model, okay, with Gaussian observations. But they're both informative ways of thinking. And the same kind of dichotomy exists for ABC. Most of the thought to begin with was algorithmic terms. How do we find a good metric, a good tolerance, and a summary? Okay. Instead, let's think about the probabilistic model. We're doing this inference. What model corresponds to the ABC algorithm we're using? Okay. And how should this inform our choices? Okay. So given that we're using this algorithm, what's the implied probability model that this corresponds to? Okay. So one thing we can show is that ABC is exact, but for a different model to the model intended. So the way to think about this is that rather than using the simulated likelihood function, we're using an ABC likelihood function. Okay? And the way we get the ABC likelihood function is we integrate the simulated likelihood function through some kernel. So pi of x given theta here is the simulated likelihood function, the probability of simulating x given theta. Then there's some other kernel that relates x to d, okay, and that depends upon the tolerance epsilon. And if we do this integral, this is the ABC likelihood. And it turns out we're doing exact Monte Carlo exact inference, but with this likelihood function rather than the simulated likelihood function. So one way of thinking about this, and the way I like to think about it, is along the lines of proposed by Mark Kennedy and Tony Hager in 2001 in another Series B red paper, the Royal Statistical Society, is we introduce reality into the problem. Okay? So we think about how the simulator relates to reality, and then how reality relates to the observations. This is normally absent. Normally we just think about, we just relate the simulator directly to the data. Okay? If we think in this term, we think about a model between the simulator and reality, a model between reality and data. We start to think about what this term could be in here. So I think about this as being a way of relating the simulator to reality, to the observations. So how does this relate to ABC? So as I say, the ABC posterior, the approximation we're getting out of ABC, or the Monte Carlo approximation to it, is what happens if we do inference using the ABC likelihood function I just defined. To simplify matters slightly, I'm going to just work in joint theta x space. So I'm going to now assume I'm going to have this auxiliary variable x, which is the simulator output. So the distribution we're always going to be working with is the distribution of the parameter theta, the simulator output x, given the data, And that is the ABC bit, the Bayesian bit that we normally expect, the prior times the likelihood. Now we've got this additional term that is the acceptance kernel. Okay. So let's see what ABC is doing. So this is just a repeat of what I've just said. And let's imagine sampling from this algorithm using the rejection algorithm. So we're going to use instrumental distribution. This is our proposal distribution in the rejection algorithm. So this is what we're going to see time and time again, that there's only really one choice in ABC algorithms for proposals. In MCMC or SMC or in rejection, we always have to have this type of proposal. Well, at least this part of it. So in this case, we're going to say we're going to pick a parameter theta from the prior, and then we're going to simulate x from the simulator given theta. And we need the simulator likelihood function to appear in here so that it cancels out in the acceptance ratio. Okay. So if we take this as our instrumental distribution, our proposal distribution, the rejection algorithm, then if we do the rejection, we get the following. Pick theta from the prior, pick x from the model, and accept theta x with this probability, which is the ratio of the thing we want and the proposal, because this is standard rejection. The key thing is that because in G we've got the simulator likelihood function, it's going to cancel out in here, and this is the bit we don't know. These two terms are going to cancel out. So this is why ABC works. So this simplifies to a ratio of these acceptance kernels. So to see how this relates to what the algorithm I had before, the uniform rejection ABC, we just make a particular choice for this acceptance kernel. Okay? If we let this be proportional to 1, if the distance between d and x is less than epsilon, and 0 otherwise, let's think about what this says. This then says, accept our pair theta x with probability 1 or probability 0. Yeah, the maximum is 1, so this is either going to be 1 or 0, depending on whether rho dx is less than epsilon. So in other words, this is going to reduce line 2 here back to accept theta if and only if the distance between d and x is less than epsilon. So we get back to the algorithm we had before. So what we've done, all we've done here by doing this, by introducing this kernel, is generalized ABC. And it's important to understand this generalization because lots of the developments come from this, okay? This way of thinking. Okay. So one advantage of thinking this way is it allows us to think about what ABC is doing. It allows us to interpret the answer we get. Okay? So one easy way to think about this is that if we've got the uniform ABC algorithm, so 1 or 0, this is a uniform distribution, right? This is saying, given the simulator output, our model for the data D is uniform on some ball of radius epsilon around x. So if we do ABC with this type of uniform kernel, then what we're getting is we've changed our model. We're doing exact inference, but rather than doing the case where we say D is equal to f of theta, we've now added an error term E, and the distribution of that error term E is uniform on this ball of radius epsilon. Okay, so in one dimension, it's uniform from minus epsilon to plus epsilon. Okay. So that may or may not be a good choice for your model. You may or may not think that relating your simulator to the data through a uniform distribution is a good thing to do or not. Okay. It may be a decent approximation if you can take epsilon small, but if you're forced to take epsilon large, you might want to use a non-uniform distribution here. Okay. Okay. So this is a key message from this bit. ABC is giving exact inference, but under a different model to the one we intended. Okay, so how do we choose this acceptance kernel? This is the last slide on this. Well, one thing, if we've got reality zeta, okay, we could let the data be reality plus a measurement error term. Okay, so pi d given x, it's just measurement error. So we don't include measurement error in our simulator, say, because that's normally a simple bit. We do it instead with an acceptance kernel. So that's one way of doing inference that you wanted to do. Another way that is often quite common, necessary, is letting E, I've called it delta here, be measurement error. We know the simulator is not a perfect representation of reality. How do we model that discrepancy? Well, let this be the discrepancy between what the simulator says and what reality does. So this is very important. If you're an oil company, you want to decide where to drill your next well, you've got an oil simulator, you know your simulator is imperfect, you need to account for the fact that it's imperfect so as not to waste lots of money. Okay, I'm going to ignore this point. So another way of viewing this, which might be more familiar to people, machine learning people, okay, is we can view ABC as kernel smoothing. So it's exactly equivalent to what I've just said, but it's common to write this acceptance kernel as a kernel where epsilon is now the bandwidth. Yep. So this ABC posterior is essentially what we get is if we integrate the likelihood through a kernel. Okay? So this is the simulated likelihood. We times it by some kernel, and we just smooth it out a bit. So this is exactly equivalent way of viewing ABC. One way is kind of a operational view of smoothing everything out, making life easier. The other way is a modeling view of thinking about what the effect is. Okay. Okay. So as you probably realized already, the rejection algorithm is a very inefficient way to do inference. We keep sampling, at least in the version of the algorithm I put up, from the prior over and over. We pick from the prior, we say, is it any good? No, we throw it away. We're not learning anything as we go. Whereas in MCMC, we do a random walk or a Markov chain and parameter space, and we learn where the high regions of high density are. So perhaps the main area of development of ABC has been on finding efficient algorithms, ways of exploring parameter space more efficiently, using the computer power to best effect. And there's a whole cottage industry, essentially, on ABC-ifying standard Monte Carlo approaches. So we've got ABC importance sampling, ABC Markov chain Monte Carlo, ABC sequential Monte Carlo, EM, EP, and so on. Okay? And essentially what you do, you replace somewhere in the algorithm the likelihood you wanted with an ABC step, where you simulate from the model and accept with some probability, either 1 or 0 if you're using uniform kernels or other kernels. Okay. So I'm going to focus here on two methods, MCMC and SMC. I'm going to assume that everyone's familiar with MCMC, but how many people are familiar with SMC, sequential Monte Carlo methods or particle methods? Okay, so not many again, so I might not spend too long on it. I'll just give you the basics, I think, for the SMC. Okay. I'm going to assume everyone's familiar with MCMC, though. So, MCMC, this is, again, pretty much the second or third ABC paper that's proposed by Paul Marjoram, a few others, and Simon Tavray again, was the final author in 2003. And remember, this is our target. This is our ABC posterior. This is the thing we're going to find, where we've got prior, likelihood, acceptance kernel that depends upon our tolerance epsilon. Okay? We want to take epsilon as small as possible. So in MCMC, we need a way of proposing moves to move around space. Okay. So we've got theta x is our augmented parameter space. We're going to propose moves in theta and x. And again, moves of this form seem to be inevitable. Okay. So to move from theta x to theta prime x prime, we pretty much need always to have an independent sampler in the last bit. Because we want the likelihood term of the simulator to cancel out. And so in order to make this bit cancel, we need to have something like this in here. So what this says is we pick a move from theta to theta prime from whatever proposal we like, so the standard MCMC. Once we've got our theta prime, we then simulate from the model using theta prime, and that's what I call x prime. Okay. So just to spell it out, this is a tutorial. Let's think about what the Metropolis Hastings acceptance probability is here. So we accept this move with this probability, so the ratio of the target at the new and old values. Okay? There should be an x in there, sorry, I missed it out. And then the moves with the direction reversed. So let's substitute things in. We substitute in the posterior terms, so substitute this in. We get these terms, these three. And if we substitute in the move for q, we get these two terms. Okay? The key point is that we get, in the numerator and the denominator, a contribution from the simulator likelihood, the bit we don't know. Because we proposed from the simulator here, it means that this cancels out, and we end up with a probability that doesn't have the simulated likelihood function in. And so we know everything in here. This is our prior, this is our acceptance kernel we just choose, and this is our MCMC move on theta. So this is something we know, we can calculate, and so we can do this kind of move. Okay. So this gives us the original MCMC kernel that we've all been struggling with for the past 10 years, essentially. At least until sequential methods were proposed. So we're going to move from theta x to theta prime x prime using the proposal queue with this, by accepting this move with this probability. Okay. But as I say, we've been struggling with this because it doesn't work very well. Okay. The probability of accepting here is very small. If this was a uniform kernel, we need to hit the data. We got lucky on the previous iteration. We got an x that was close. But to get a new x prime that is close to d, we found we get stuck in this position for a very long time. Okay. So generally, we found these methods don't work very well, these MCMC methods. And so we'll talk about sequential methods that have replaced them really in a minute. But I just want to talk about a very new innovation in this first. So first note, for those of you who are into Monte Carlo type of methods, this is a pseudo-marginal Metropolis Hastings algorithm using the language of Gareth Roberts and Christophe Andrieux from a couple of years ago. Because what we're doing, we're estimating the likelihood in here. Okay? And it turns out that estimating this likelihood turned out to be an okay thing to do. Okay? It's essentially the message of the paper. We can modify it to try and improve the mixing by, instead of simulating once from the model, simulate n times. So we get our new theta prime, we simulate n realizations from the simulator, and then we, instead of having just one acceptance term in here, we're going to have the sum of n of them, and that's going to help get an average acceptance rate, if you like. And this helps smooth things out a little bit. Okay. So there's been a recent development this year and last from Anthony Lee in Warwick, and then I think he's moved to Oxford now, that I think it's going to be very successful. Okay, so he proposed a new type of MCMC kernel he's called it a one-hit kernel. So the important line here is line 3, but essentially what we do is the same as before. We pick a theta prime, depending on where we currently are, accept it with some probability. That's just the ratio of priors and the proposal bit. So if we've got symmetrical proposals and uniform prices, it's going to be 1. So we always accept here. This is the key new bit. What we were doing before was saying, sorry, where have I gone? Simulate a new x and just accept or reject. Simulate one new x prime, accept or reject. What he said we should do instead is the following. If we've got theta where we currently are, and theta prime the new theta, do 2 simulations. Simulate a new x using theta, and a new x prime using theta prime. Okay? And see if any of them get close to the data or not. Are we close to the new one, or close to the old one? If not, do it again. 2 new simulations, a new x and a new x prime, from the old value to the new value. And keep going until one of these hits the target, gets within our ball of radius epsilon. If it's the new one that accepts, if x prime is close to d, we're going to move. The new parameter value is going to be theta prime. Otherwise, we stay where we are if it's the old one that accepts. So this is the important bit, that is able to show that this new kernel has properties that the old kernel does not. And is able to show something we didn't know before as well, that this old kernel, the Marjoram MCMC kernel, had a couple of properties that we don't like. So this is a little bit technical. We'll be off it in a moment. The first one is that there's 2 properties, variance bounding and geometric ergodicity. So variance bounding basically says, is there a central limit theorem for estimates from the chain? Okay. So if we've got a running parameter estimate of some quantity of the posterior, so it could be the posterior mean if H was the identity. Okay. So we estimate the posterior mean as we go along the chain. Okay. Is the variance of our estimator small? So it turns out that for the Marjoram kernel, it's not small, and for the one-hit kernel, it is small. Okay. The other property is geometric ergodicity. So if you don't know what this is, it basically says that if we run the chain long enough do we get close to the target quickly? So the distance between the MCMC distribution that we're getting, the target distribution, does that distance vanish at a geometric rate? Does it go to zero at a geometric rate? That's a desirable property that we want to converge quickly. And if we don't have this, it says that our chains converge slowly. Okay? So it turns out again that the marginal kernel isn't not geometrically ergodic, whereas the one-hit condition is. One-hit kernel is subject to conditions. So what this means in practice is that some of the problems we've been seeing with MCMC ABC are down to a poor choice of proposal and of acceptance of MCMC kernel, basically. So these results are from Lee et al. 2013, and it's just done the same thing, the same MCMC algorithm with different kernels. So this is the marginal one, and it's just got a running estimate of the posterior mean. So the posterior mean is the black line in here. Then he's done it with multiple simulations from that kernel. Okay, and we do a bit well, I'm not sure if that's any better or not. And then we do it with the new one-hit kernel, and it turns out that it's working a lot better in certain situations. So one thing to note about this is that it does require significantly more computation because we have to keep simulating around this step for each iteration. Yeah? So it is going to require more work, but the signs seem to be that it's worth it. Okay? By doing this extra simulation, we're gaining by doing this. Okay, so that was a bit technical. So something about a bit lighter on importance sampling, and then we'll have a break. Okay. So if we're using non-uniform acceptance kernels, then we can do importance sampling at ABC. So again, we pick from the prior, we pick from the simulator, and now we're going to give theta xi a weight that is proportional to the acceptance kernel weight. Now, if this was a uniform kernel, this would be 1 or 0, and it's essentially rejection again. We're keeping it or we're not. If the weight's 1, we're keeping it. If it's not, we're rejecting it. And it's easy to show that importance sampling is more efficient than rejection sampling. So if we can afford to do the importance sampling for memory reasons, it's expensive, then it's better to do importance sampling than rejection sampling because we're not throwing away information. It's essentially every time in rejection sampling, we're accepting and rejecting with this probability. Instead, we're just storing that probability, and we lose less information by that extra bit of randomness. Okay? Then I'm going to skip that. I'll just come on briefly. What this says is that the problem with this is that we have to store a lot of particles that are very small weights. Okay? So we quickly run out of memory capability if we store everything and its weight. So there's kind of a cross between rejection and importance sampling. And essentially what we do, we set some threshold, and if the importance weight is less than that threshold, we accept or reject the move with this probability, so the value of the weight divided by the threshold. If the weight is bigger than the threshold, we automatically accept it. So this gives us a way to kind of thin things out and get rid of useless particles, essentially. Okay. So these two ideas we need for sequential ABC. So the sequential algorithms are really what's been the driver of ABC in biology, I think. Well, as I'll say after the break, there are two main approaches. One approach is what I'll talk about after the break with regression adjustments. The other approach is efficient algorithms, and generally that means sequential ABC because we didn't think the MCMC version worked very well until recently. Okay. So there's three papers that kind of propose this at a similar time. Sisson et al. From 2007 was really the first one that wrote down the first sequential sampler. There was a small mistake in this, which was corrected by Mark Beaumont and Christian Robert and others in 2009. And there's another kind of paper from Tina Toney and Michael Stumpf in 2008 in bioinformatics, I think. Maybe it wasn't bioinformatics, a biological journal that did essentially the same thing. So this paper, well, they've all proved very popular, but this in particular has been noticed by the biologists, and so lots of people working in similar areas to Michael Stumpf, so bioinformatics and systems biology, now use this kind of methods. So I know not many of you know about sequential methods, so just very briefly, the idea is that we're going to sample from sequentially from a sequence of distributions. So we're going to start off with some distribution that is pretty poor and go through a sequence of distributions until we get to a distribution that is our target distribution. And we hope that, well, we're going to design it so that these are close together, so we've got small steps to go. And in each step, we're going to have n particles from each distribution. Okay, so I've got for ABC, what this means is we're going to have a sequence of tolerances that get smaller. So we're going to start off with a distribution that has a large tolerance, so it's a bad approximation. We're going to make it a bit smaller to get a better approximation, better, until we get to where we want to be, or the best we can do. Okay. So this is the idea. Maybe we start with the prior. We have our first distribution, which is quite dispersed. It looks quite a lot like the prior. And we're going to shrink it by making epsilon a bit smaller, until we get to our target, which is as close as we can get to the posterior as we can. Okay? So this is a picture I've just shamelessly stolen from Tina, Tony, and Michael Stumpf, okay, 2010, from their tutorial. So in other words, what this means mathematically, we're going to have this sequence of targets, and the only bit that changes, the only bit we can change, is the acceptance kernel. Okay? So this acceptance kernel, we've just got epsilon to get smaller and smaller, and we're going to try and approximate these things. The likelihood has to stay the same because we need it to cancel every time.
Question?
Yes?
So why
Zoom in.
at that epsilon, why not go to the true distribution somehow?
Because we can't. In practice, degeneracy kills us way before we get to the true answer. Okay? In practice, because we still have to do simulation, so we just the degeneracy of the particle filters just blows up. You don't have to go very far to find this either. It really is a problem. Okay. Okay. So this is the idea. At each stage, we're going to have a particle approximation that approximates our distribution. So again, this is a bit technical, I apologize, but it's the only way of writing these things down. So we've got a particle zt, that's our parameter, and our simulation value, theta and x, and it has a weight corresponding to this. Okay? And we approximate the posterior by this weighted sum. So the way of thinking about this is we've got an empirical distribution function, a step function for each particle. Okay? And the steps are different sizes if we've got different weights. And if we differentiate the step function, we get this sum of Dirichlet delta functions. So in words, what the algorithm is doing is we have a collection of particles for the first distribution, epsilon 1. Okay. We're going to move each particle in some way. Then we're going to accept or reject the moved particles according to population 2. And we're going to get a new set of particles 2. Okay. We're going to move them again in some way, depending on where they are now, accept or reject. Move them in some way, accept or reject. And we're going to hope we get, at the end, get a collection of particles that closely approximates the thing we want. Okay. So this is, in words, what I've just said. So suppose we're at step t, so we've got our particle approximation to pi t. First thing we do is pick a theta from our previous population according to the weights. So just randomly pick with replacement according to the weights. Perturb the particles in some way. So this could be a mark of, well, here it's just any old random walk move or independent sampler, if you like. Okay. So pick a new theta prime. Reject theta prime if it has 0 prior density. If it doesn't, simulate. And if the simulation is close enough, we'll accept the particle. If it's not, reject the particle. The new weight is this kind of slightly complex looking expression here. We just keep going round and round this until we have n accepted particles at time t. So in this formulation, even if epsilon's too small, we just have to keep going around here forever. Yeah? We're just never going to get to where we want. Okay. So I wasn't very aware of what this audience was going to be in terms of how hardcore Monte Carlo or not, but I think given that many people haven't heard of SMC, I'm not going to go through the next few slides and focus more on the second half, the modeling and the machine learning type things, because these are very technical. So I'm going to skip a few slides, but essentially there's been an awful lot of work on developing different sequential Monte Carlo samplers. This first one by Tony et al. Is very naive in a couple of ways, okay? And we can improve it by doing better choices here, by different weightings here, and being slightly cleverer about what we do. Okay. And there's one way of understanding it, which all comes from the Del Moral et al. 2006 paper. But if you're not familiar with it, it's quite challenging. So I'm not going to go through it. Okay. Okay. So just to conclude, and I've got one more section before a break. Our tolerance epsilon controls the accuracy of our ABC algorithms, and so we want to take it as small as possible, but we can only take it small if we've got efficient sampling algorithms. And essentially that means exploring space better. Deciding where to run the simulator in a smarter way determines about how good an approximation we can do. So these MCMC or SMC versions of ABC are essentially that. They're smarter ways of finding good parameter values. And in practice, people use this most of the time, this SMC, or they do what I talk about after the break, one or the other. Okay, so just a couple of slides on links to other approaches. So the first one is history matching. I don't know how common, again, history matching is, but it's very common, say, in the oil industry. So you've got a sequence of wells, and you want to predict the flow from the different wells over the next year so you can control your revenues and decide whether you're going to sink a new well or not. Okay? So you have a model of the oil reservoir, okay? And there's lots of unknowns in this reservoir, unknown geology and so on. Okay? So there are lots of unknown parameters in the model. So what they tend to do in the oil industry is what's called history matching. So they first go through the step of relating the simulator to reality. So they sit down with their experts and think, how good is our simulator? Where's it going right? Where's it going wrong? So this error term might not be additive, and it's probably got inputs of its own, but we think about this discrepancy. We then relate reality to the data, the measurements we're receiving. Then we do the history matching step. So we're going to call theta implausible if the distance between our data D and our simulator run at theta is big, okay, bigger than, say, 3 sigma or 5 sigma or whatever, some rule here. Okay? Where sigma is just essentially the sum of the variances from how well we think we're doing. So the reason I wanted to say this is I think this link teaches us something about what ABC methods are doing and perhaps what we should be doing when we do calibration, which I think is often ignored. So the output from the history matching is to say that theta is not implausible if we don't discard it. So it's typical statistics here. Rather than saying it's plausible, we're saying it's not implausible. I don't want to be too optimistic. Right? And so what we've got is a region of space we can't rule out. But one answer from the history matching might be that we rule out all of space. So we go through our history matching and we find no parameter values theta that are any good. Okay? So what does this tell us? It's essentially that we need to go away and think harder, that something's misspecified. Either our simulator's too poor, our data are noisier than we thought, or we've got this discrepancy wrong. We've been overconfident about how good our simulator is. Go away, do it again, come back, and then we'll talk some more. And this is kind of what's happening in rejection ABC. If you set your tolerance too small and you get no acceptances, what this is saying is that there's something misspecified in what you've done. Your acceptance kernel is trying to be too tight, you're trying to be too confident about how good your simulator is. Your prior is wrong, or whatever it is. Go and think some more. So in contrast, if we're using a likelihood technique or a fancier ABC technique, we're always going to get an answer. So one of the problems we find in kind of computer experiment literature is that if you use MCMC, you get this posterior out, and you have to be very careful to check that the values you found are good values. MC will just tell you what the best values are. It doesn't tell you whether they're any good. So I like the aspect about ABC and history matching, that it's made you really think about this link between model and reality. How are we doing? Okay. I think I'm going to skip this as well, because I skipped the other bit. Okay. And then finally, there are lots of algorithms, as I say, in different communities that are essentially ABC. Either ABC's re-embedded them or they've re-embedded ABC, depending on how you view it. So Simon Wood had a Nature paper, just purely statistics in 2010, which is essentially an ABC algorithm. He just used a particular choice for the acceptance kernel, multivariate Gaussian, and he summarized it with a sample mean and covariance. He hadn't realized it was an ABC algorithm at the time, but it worked very well in his ecology problems, so he kind of reinvented it. If you work in hydrology, there's a very popular type of methodology called glue, and again, this is ABC, and I could have listed lots of papers here that are basically saying reinterpreting algorithms as ABC. Okay, so let's just have a 5-minute break. So we're starting at 5 past now, give people a chance to stretch their legs. But what we're going to do in the second half is talk about alternative approaches to ABC. It's about summary selection and about modeling the error in your ABC, and it's a bit more machine learning type material. Yeah? So we'll start again at 5 past 2. I'll ask people now. Yeah, of course. Yeah, absolutely. Yeah. So it depends again on the form of the album that you've got. So in the album I put up, the resampling done automatically because you keep picking with replacing computer population. That's kind of forcing you to do resampling every single step. And so resampling there isn't going to cure your degeneracy in any way because the weights, I mean, they weren't 1, but the bit that you resampled hasn't changed. You know, so that bit is 1 already. It's kind of also already resampled. In the more advanced versions of SMC, resampling definitely makes a difference.
I see, but so that's true. But in the case that you chose, can you also use it for intractable, for example, or was it like the distribution you're trying to sample stationary? Is this something that you?
No, it can definitely. So there are these sequential approaches for dynamic range, so filtering approaches. Yeah. So Singh and Doucet have done various written various papers on this. So I think in some ways the natural.
But also in this case where you don't, well, as far as I understand, you use this ABC and you don't know what the likelihood is, right? That's when you have this complete intractability or.
Yes, that's right.
So, but I think in the case of this album, he knows knows the likelihood of observed constant, right?
Possibly. He has done some ABC things as well. But essentially what we're doing is we treat the ABC likelihood as the known likelihood, although you've got this unknown significance. So, yeah, most of his work is absolutely likelihood-based things, but he does have non-likelihood things as well. I'm not sure if it's the same paper. There was a Singh paper with people and a Doucet paper with people. What I'll do, I'll put the slides on my website and I'll put all references
Yeah, that'd be great.
on there. But yeah.
Curious how long you're staying around UNC.
Yeah, they always get.
All right, good.
So yeah, you had some thoughts on.
Well, I'd be very interested to talk to you. Probabilistic programming is very related.
Right.
Slightly different. I mean, from a pure science standpoint, simulation gives you a probability measure. It doesn't necessarily give you a density with respect to some denominating measure. Like
right.
You have a saying, you know that. Anyways, yeah. So but of course, if you have a simulation and computing that probability measure or say a density associated with it could be like extremely expensive. So, I'd say that maybe the difference is normally when people say. I mean, I guess I also don't like likelihood grading because there generally is a likelihood on a much larger space.
Yes. Yeah.
And then the likelihood, because they're nuisance parameters, the likelihood is this integral.
Yeah.
But of course, a lot of techniques like MCMC can run a higher dimensional space and just throw away something.
Yeah.
Samples from a marginal.
So I saw a talk with a paper by Peter Neal, who was doing the branch process one I put before. They've done it by MCMC exactly. So they keep all their uniform random variables that go into it and do MCMC on a 100,000 dimensional space. I'm skeptical about how well that can mix, but his results are brilliant. So,
So what is that?
well, sorry, they are the computational savings are factor of 2 only. What the sense that they're brilliant are they are very close to the ABC results. If you know what I mean. It's hard to know.
Yeah.
It's hard to know without having tried it how. You know, if you've got a 100,000 dimensional space and you're doing a million moves, how often is a move?
That's right. Yeah. Yeah. So probably some very usable, that with very high dimensional spaces, usually millions.
Oh, really?
And there is. Oh yeah.
Yeah.
And there's. But then there is the problem that if you're not smart about the moves you make, then it's problematic. And then so some ideas there are these very like moves that change many variables at once. But then of course if you do that naively, you get a really bad proposal and reject it. And so people have ideas for how to shore that up. Anyways, yeah. I don't want to talk to you about give you time to do for the second half, but I'd love to be really great to sit down and
we should.
We can get dinner and lunch.
Yeah, absolutely. That'd be great.
Anyways, so far so good. I'm curious whether you're going to talk about how you choose the distance function.
I'm not actually. The distance function.
Seems like you'd want. I would think that information geometry or something would
I've got one slide on it, only about what happens if you pick a really bad choice. But as far as I know, no one's really looked at it. I mean, the way I think about it is this acceptance kernel, which is a model between your output, and so that kind of moves the goalpost, if you like, of what you're thinking about. So I think about that one instead. But if you're doing with just distance, how you pick a good distance, I don't know.
Yeah.
I'm not sure I've seen anyone really say anything about it.
Yeah. I was at ABC in Rome.
Oh, were you?
Yeah, and I asked a few people. There was a talk or two about the distance function, and there's some relationship with generalized moment methods, and that people have pointed out between ABC as like sort of a sampling version of generalized moment.
Right.
And in that work, it's common to like use a score function as a distance measure.
Yes. Okay.
Which I mean that sort of.
That's my point.
To my mind, to my mind,
yeah.
something like something having to do with the information geometry of the space sounds like the right thing to do, but I'm just not aware of any.
So I wasn't aware of anyone having which one. So I've been making the point for a while, but proper scoring rules as summaries are a really good choice.
Yeah.
But as far as I know, no one's written anything, but maybe they have. I did see something on the archive a week or two ago that the abstract sounds along those lines. But,
this was this guy Imperial UCL. No, it wasn't me. I actually had an email back and forth.
Oh, good.
No? Or not? Give him too little time.
No. Often probably not in the room. I really didn't know, I've not been to these companies before, I really didn't know what machine learning is. I have no idea what the area of interest is.
Yeah, I mean, it's some people argue that it is statistics.
Yeah,
but
well,
I think it's a little, the aesthetics are very different.
Right, yeah.
I think statisticians often, the work you're talking about is circular in this boundary between computation and the model.
Yeah.
Right. I mean, if a statistician is studying some models and they generally don't like inference algorithms, which makes some sort of uncharacterizable change to the model, but still yields good empirical results. Like to machine learning person, that's perfectly reasonable.
Yeah.
Like variational techniques, things like that.
Yeah.
For the statistician, where they can no longer say that the answers kind of have characterizing what they have to do with the model they wrote down, very problematic, and like also in sciences, etc., where you want to make some kind of claim this model is a good model, like, and again, like making some kind of very coarse perturbation model in order to get efficient inference is not something that's allowed. Whereas in machine learning, I think there's more of an end-to-end
empirical evaluation is a key part of that. Indeed, like it's it's a non-parametric way, if you will, of like testing if your procedure is like good there, it's working. It's like something.
Yeah, it's not something good. It's thinking about whether the model's good, but not whether the inference is good or. They're all separate issues, and people often don't check whether the model's good because the answer's just the answer. It's conditional upon the model, and that's the end of it.
Whereas, I'd say you could have that's a subtlety. I think there's pockets of people who have very much like statisticians, people who don't care about models at all. It's just empirical. There's a wide range from extremely theoretical to very applied. So it's maybe culturally it's heavy. I'd say. Yeah. And so there's a less on that. So like the aesthetics, like you look at the way math is done in machine learning, it looks more like a bunch of physicists. And then there's like second generation people who consider themselves machine learning, look at the first generation of papers, like the first 20 years, and are kind of mimicking that. The aesthetic of the first years is physics as well. It's not a rigorous math. So that's what I would say makes a difference.
Interesting. Shall we start again?
We're going to start. There's no one paying attention. Are you mic'd?
Am I mic'd? No.
We're going to start in a moment. Maybe I'll go outside and try to round people up.
Okay. Okay, shall we get started again? So, very quick recap of what the uniform rejection algorithm is, because that's all we're going to be doing for this part. Okay? So, we've got pick from the prior, simulate x from the simulator, accept theta if the distance is small. Okay? And so we've looked at efficient algorithms. We have a completely different approach that is correcting the algorithms we've used. How can we do post-processing? So the first thing is just to call this cursor dimensionality. If the data are too high dimensional, we're never going to observe simulations that are close to the field data, okay, to the real data. So we use this ABC as summaries instead. So we now accept theta if the difference between the summary of the data and the summary of the simulation is small. Okay. I'm going to change notation on you just to confuse you. Now I'm going to call S obs the summary of the real data and S the summary of the simulator, just so I don't have to carry around this clunky notation a bit. Okay. So there's two kind of main ideas here. One is using summary statistics. The second idea is regression adjustment. So we're going to build a model to account for the discrepancy between the observed summary and the summary from the simulator. Okay. So first of all, regression adjustment. So this is kind of a post hoc processing of the output you get. Typically, people run their rejection algorithm, so the simplest form of ABC, run it for a week or 1,000 hours or how much time they've got. Okay? So if you have a large cluster, this could be a very long time indeed. Then they do a regression adjustment to try and do something better with the information they've got. Okay. So what we're trying to do is a post hoc adjustment of the parameters to weaken the effect of this discrepancy between S and S obs. And there's two key ideas. One is kernel density estimation to emphasize the best simulations. And the other is to learn a nonlinear model for the conditional expectation of theta given S, okay, as a function of S. And then we're just going to plug in S obs, the observed value of S, to try and get a better estimate of this posterior and of the density. So the first idea, kernel regression, is very closely related to what we had before. So suppose we want to estimate the expected value of theta at the observed summary. Well, this is just the integral of theta times the posterior. So probability of theta, density of theta given S. And the posterior can be written as the ratio of two densities. And we can estimate both of these densities using a kernel density estimator. So if we pick pairs theta I SI from the model, so just simulate theta from the prior, S from the simulator, we can then do a kernel density estimate of both of the things in here. So the joint density of theta and S, we've got a kernel term in S, kernel term in theta. Same in the denominator, just we've already got S now. And if we just substitute these in and don't worry about what we're doing, we get what's called the Narad-Dyer-Watson estimator. And we get the expected value of theta given S is now a weighted linear combination of the thetas. Okay? So each theta I from our simulation now has some weight, where the weight is the kernel for that term divided by the sum of all the other kernel weights. Okay. So this was kind of the other key early ABC paper by Mark Beaumont, David Boulding and others in 2002. And as I said, there's two main streams of research, people who do this and people who do the efficient algorithms. And they come together increasingly, but that's broadly what was happening. So Beaumont et al. Suggested using an Epinetchnikov kernel here, primarily because it has finite support. So if we get further enough away from zero, or further enough away from the data, this weight goes to zero, so we can throw it away. If it has zero weight, we don't need to store it in memory. So they then just recommend picking an epsilon to keep a certain proportion of the results. So pick epsilon so that you keep the best 5%, say, of your simulations, or best 10%, and then give each one a weight. Another way of understanding what this weighting is doing is it looks exactly like the importance sampling we had before. The importance sampling we had before said that we're going to approximate the posterior as a sum of weighted particles. Okay. If we let the weights be these kernel weights, then it's exactly equivalent to what we're doing. Okay, so there is kind of coming together of these two approaches. But the key thing again is that this estimator suffers from the curse of dimensionality. This kernel density estimate, if S is high dimensional, is going to become pretty poor pretty quickly. Okay. So the key thing is finding a low dimensional S, or correcting. So one idea is regression adjustment. So this is also from the Beaumont paper, 2002. So we're going to try and model the expected value of theta given S as a function of S. Okay? So I'm just going to call this term the posterior mean of theta M of S, and we're going to try and learn this model M of S. So we can think of this as a model for the conditional density of theta given S. So for a fixed S, if we had draws from this density, we're going to get theta I of the mean plus zero mean errors. Yep. This is our model. So we've got the zero mean uncorrelated errors. How do we learn M? Okay. So, well, we'll talk about how we learn M in a minute. Let's suppose we've got an estimated model. So M hat of S is our best estimate of the model from our samples, theta ISI. The first thing we can do is more accurately now estimate the posterior mean of theta at the observed summary. Yeah? If we plug in the observed statistic into our model, we're taking strength from all the simulations, not just the ones that exactly matched S. So I've got some pictures that help explain this in a minute. Okay. This is the first idea, that we can improve our estimate of the posterior mean by just plugging in the observed statistic to our model. The other thing we can do is form the empirical residuals. So again, I'm in danger of using statistical language rather than machine learning language here. But if the residuals are the difference between the true values of theta we simulated and the fitted model, and they tell us how good the model is, we can then approximate the posterior by adjusting the parameters, by taking the fitted parameters and adding on, taking the fitted model and adding on the residuals. So this gives us a sample that we think about as approximating this posterior, okay, by taking the fitted value and adding on these empirical residuals. And we can view this as just moving the parameters. We've taken our original parameter, theta I, and moved it according to how good the model is, how close the model prediction is for the observed S from the simulation and the observed S from the data. So this is much clearer in pictures. Let's have a picture. Okay. So this is the same as the pictures before. I've swapped the X and Y axis to reflect the direction of the modeling here. So we've got the summary on the X-axis. We've got theta on the Y-axis. So each dot in here is just a simulation from the prior and then from the simulator. I pick a theta, I then simulate a value of S. Okay? And so there are all the dots. ABC, we've got the observed value of S, that's this red line, and ABC says take a ball of epsilon on either side and accept all the points in the middle. Okay, so they're the red points, exactly the same as before. So what this approach says is let's build a model for theta as a function of S. Yep. So that's the green line. Let's fit a linear model here. It happens to be linear in this case. Okay. And so that's our fitted model. We can then estimate the value of theta at the observed value of S by taking this slice along here. We can estimate the posterior mean by taking the value of the prediction of the model of the green line at S obs, so the point here. And then we can form the distribution by taking the residuals from all these points. It's hard to point. If we look at the distance between the red point and the green line over here, this is a residual. And then we translate them all up over here. So ABC is going to have a very broad posterior because it just shrinks all of these on. So we values of theta between here and here are allowed. But by the time we just look at the residuals, none of the residuals are that big of this model. So we just push them all up to here, and we adjust the parameters in that way. So that's essentially what's happening here. Okay. So we've got a parameter over here. It wouldn't have been accepted in this case, but we've got a parameter over here, and we just move it along. It's the same distance between the line, the green line, and the point when we translate it down to here. Okay. So that's going to help us. We might not have any points along this line, along their SOBs, but by drawing strength from the observations nearby, we can get a better approximation. Okay. So the Beaumont et al., 2002, not 3, used a local linear model for MOS. So they just fit a linear regression in the vicinity of the observed value of S. Okay. So to make it locally linear, they minimize the sum of squares times by the kernel. It penalizes you if your S is too far away from the observed statistic. Okay. So that observations nearer to the data are given more weight in the fit. Then because we've got these weights here, the residuals are also weighted. And the residuals are just these terms once we've fitted the model. And so we have to weight the residuals when we shift them along. But you don't need to know that. Okay, so I just wanted to demonstrate how powerful this is. I come from more the Monte Carlo side of things, so I tend to use the fancy algorithms in the first part. That's really what I'm interested in. And it's astonishing when you try this, how effective it can be. So it doesn't really matter what the model is here. It was a very simple toy model. I just had a normal likelihood with a normal prior. Okay. I just generated 200 observations. The red line is the ABC estimate of the posterior. The black line is the true posterior. And then with my ABC output, just applied this regression adjustment, and you go from something that's far too dispersed, okay, a bit wobbly, to something that's almost exactly correct, the dashed line that lies pretty much on top of the true value. So these regression adjustments, when they work, and they work most of the time, are very effective. Okay? They can greatly increase the accuracy of your posterior without having to resort to all these fancy algorithms. Okay, so extensions to this, I'm trying to highlight things that might be of interest to machine learning people. We can do all kinds of fancy modeling to get a better fit here. And it hasn't really been very looked at because it's not particularly the focus of the statistics community. But one type paper by Michael Blum and Francois in 2010 changed from the homoscedastic model I had before to a heteroscedastic model. So homoscedastic means constant variance, heteroscedastic, non-constant variance. So what we had before along this pic is the variance of the residuals at any point are constant. It happens to be true for this data. Okay. But in general, it might not be true. We might find that for small values, for some values of theta, the variance is very large of S, but for other values of theta, the variance of S is very small. Okay. So they fit a model for the mean and for the variance, and I think they use feed-forward neural networks here. And because they've done this, when they adjust the parameters, you have to kind of re-weight the empirical residuals to account for the fact that you've got different variances. So their fitted model is this green line. So this is a picture copied from Michael Blum, where now you've accounted for the fact that the variance grows out here. Okay? As theta get large, the variance. And again, this can be very successful, but trickier to make work. Okay. So as I say, I think these methods are underexplored and not used often enough in ABC at the moment. They can be very effective, but as I say, people tend to split into two crowds: those who do rejection and adjustment, or those who do sequential Monte Carlo. The other thing is that modelling variance tends to be hard, so a key to making these methods work is to apply transformations to make the model as homoscedastic as possible. So typically things like box-Cox are applied to try and make everything look constant variance. Okay. Okay, so this is the final main section. I've got a couple of slides on a research bit at the very end, but this is about how do we choose summary statistics. So there's a very good review paper that helped me write this by, again, Michael Blum and others. And they point out that the error in the ABC approximation can be broken into two parts. The first part is the choice of summary. If we summarize the data by some lower dimensional summary, we're throwing away information. This is compression of some sort. How close is the true posterior, given all the data, to the posterior when we condition on the summary? So that's one source of error. The other source of error is the use of our ABC acceptance kernel. So we've got the true posterior of theta given the summary. How close is that to the ABC posterior when we filter it through some kind of acceptance kernel? We've got the metric, and we only accept if the distance is small. And what they point out is that there's a trade-off between these two errors. If the dimension of S is small, this bottom posterior is this bottom error is likely to be small as well, because the dimension of S is small, so we're probably going to be able to get close to it using our ABC. The cursor dimensionality hasn't kicked in, so we can do well here. But we're going to do badly here. If the dimension is small, we've probably thrown away a lot of information. Conversely, if the dimension of S is large, this approximation will be good, because we've kept most of D. We've not lost much information. But this approximation, we're trying to now match objects in high dimensional space. It's going to be difficult. So this approximation may well be poor. So there's a trade-off. Okay. So how do we choose good summaries? I said this before, but it's worth repeating. First of all, if the summary is sufficient for theta, i.e., one way of writing sufficiency is if the posterior is the same, then this is obviously having no detrimental effect. So that's the ideal. We want summaries that are approximately sufficient. But we can never find low-dimensional sufficient summaries for the problems we're applying ABC to, because if we could, we wouldn't be doing ABC. Yeah? If we could do the calculations to say whether a statistic is sufficient, we could do enough to not have to use ABC. And if we can avoid ABC, we should. Okay. So again, I think this is an area that there are lots of papers on statistics, but it just feels like the kind of area that machine learning people are very good at this kind of methodology, and it'll be interesting to see what could be done. Okay, so these are kind of a selection of the most popular, I guess, summary selection methodologies. They're kind of broken down into groups. I'll just talk about two of them, really. So the first kind of group is best subset selection. So we're just going to have some criteria, and we're going to search through the possible choices to see what the best choice of summaries is. The other is a projection approach, and there's a very popular and influential paper last year by Fernhead and Prangle. that we'll talk about. And finally, there's a regularization approach in this paper that seems to be very successful. It's essentially taken these approaches and adding on a penalty term for having too many parameters. You add a ridge regression or a lasso type of penalty, L1 or L2 type of thing. Okay, so we're going to assume all the time we've got a candidate set of summaries, S1 to SP, and we're going to want to choose from them. How we get this candidate set is a different question, which I want to talk about. Okay, so the best subset selection basically works as follows. So we introduce some sort of criterion. So there's two common ones. First one, the second one is entropy. So entropy essentially measures how much uncertainty there is in theta once you've conditioned on the data D. So how sparse is your posterior? And you want to minimize the entropy. You want your posterior to be as informative as possible about the parameter. That's what they argue. I'll give a caveat to that in a moment. The other is this torse efficiency. So what they look at is the difference between the information. So this is notation S. The colon means all the summaries from 1 to k. Here. So if we take all the summaries from 1 to k and look at how much information is there, the density of that given theta, and the same for the difference between 1 to k minus 1, where we've already got the first k minus 1 summaries, and look at this difference, and then look at the maximum and minimum value of theta. If that difference is small, less than tau, say, we're going to say that sk is not informative about theta compared to the first k minus 1 summaries. And so therefore we don't need to bother including it. So we have this criteria we can evaluate in either case, and we're just going to implement this within a simple search algorithm like forward selection, for example, or backward selection, or any kind of greedy algorithm. What are the problems with doing this? Well, the first one is that it assumes that every change to the posterior is beneficial. That's not necessarily the case. You can have daft summaries that you include that are influential about theta, but there are good modelling reasons to think that you shouldn't be using them. They're spuriously informative. We don't necessarily want a tightly constrained posterior. In fact, Neil Lawrence is always telling me that if you can estimate your parameters too precisely, that you probably got your models misspecified somewhere. You need to make your model better, and you need to be more uncertain about it. The other big drawback of these methods is that there's considerable computational effort required to compute either of these things. In each case, we need to know something about the posterior or the likelihood. So what it means again is that it rules out doing SMC or MCMC. We have to use rejection, because if we use rejection, we can just change the summary and use the simulations we've already got and stored. We just do the same analysis with the simulations we've already done with different summaries and see what happens. Okay. So these were the two main papers, Joyce and Marjoram and Nunes and Boulding, until last year, when Paul Fernhead and Dennis Prangle again had another Series B red paper at the Royal Statistical Society, where they talked about projecting S onto a lower dimensional, highly informative summary. So the idea is we've got lots of terms in our collection of summaries S. We might need to use lots of them to get the same information content that could be contained in a lower dimensional combination of them. So can we combine the elements in S in some way, linear or non-linear, to get something that's informative about theta? So what Fernhead and Prangle did, they said that most people are trying to get a good approximation for the posterior. So in other words, to find the ABC posterior given S to be as close as possible to the true posterior given D. And so it's too difficult. Let's weaken this requirement and instead just try and find summaries that lead to good parameter estimates. So if we just want to estimate some function of the parameter rather than the entire posterior, it makes life a bit easier, and they could do some of the calculations about what the optimal choice was for the summary. So they introduced the posterior, they introduced a quadratic loss function that said if the true value of theta is theta true, and we estimate it by theta hat, we've got a quadratic loss. Okay. How do we minimize the expected posterior loss? And what they were able to show was that the optimal summary statistic, S, is the posterior distribution of theta given the data. Okay. Which isn't, again, that surprising. But I don't think we didn't know that before. That the best thing we can do here is take the best parameter estimate, because obviously if it's posterior loss, the best parameter estimate is the posterior mean. So the best summer we can use is that best parameter estimate. Okay. Now we don't know this. We're trying to find this. We don't know this. Okay. So what they tried to do is introduce this regression modeling, or a similar kind of regression modeling, to get an estimator of this summary, and then use that fitted model as their summary. Okay, so this is very similar to what we had before. This isn't known, so let's model it. So they can have a different, slightly more richer class of model. So we've got, we assume that the theta i's, the simulations we have, are draws from the posterior, are the posterior mean plus errors, basically. Okay, so we've got the posterior mean theta plus some zero mean errors, and that gives us our desired posterior for theta. So let's assume a model in terms of S here. So now, because they've got a different situation, they can have a non-linear model in the S's. So they just let f of S be some sort of vector of functions of the candidate set. And they do a small ABC pilot study to try and choose the best choice of this model here. What elements to put in S. So choose it using BIC or AIC or anything like that. They then use the single summary that is the fitted value of their model at the observed statistic, okay, for theta. So for each parameter, they've got a single summary. And they showed that this trade-off we have between high dimension and low and accurate summaries, in this case, if they're only trying to do point estimates, it's best with a single summary per parameter, and that this is a good choice. Okay, so the advantage of this kind of approach is that it scales very well with large P, so diameter of theta, okay, dimension of the number of summaries you have. And it gives excellent point estimates. Okay, that's why it was designed. So of course it gives good point estimates. The drawbacks, again, are usually that it lacks interpretability and doesn't say anything about how good the posterior distribution is going to be. So if you really care about the posterior, you can find the posterior using this, but the theoretical underpinnings tell us that this gives us good point estimates, not good posterior estimates. Okay, so this is my slide on warnings about automatic methods for summary statistic selection. Okay. Generally, they're a very poor replacement for expert knowledge. Personally, I think it's much more useful to think what aspects of the data do we expect our model to be able to reproduce. This makes more sense if you're doing science, so working climate modelling. We know our models can reproduce global average surface temperature. We know they can't reproduce cloud cover or precipitation. So depending on what we calibrate them to, the summaries should be what do we expect them to perform well on. The problem with some of these summaries is that you can have summaries that are highly informative about the parameter, but if your model wasn't designed to predict them, they can be spurious, give you spurious confidence. So imagine you've got a dynamical system. So I work on ice age models, modeling interglacial cycle. Now the models are designed to pick up periods and amplitudes. Okay? They're not designed for phases. So if you use a summary that is not phase invariant, it depends upon the phase of your simulator output compared to your model, you're going to get spurious level of accuracy that is undeserved. So you have to be careful, and you have to, the summaries you put into these methods have to be summaries that are sensible to use for the model you've got. Okay. I said this before, but I'll repeat it, that generally we can't do these kind of things with the efficient sampling algorithms because we have to rerun the MCMC or SMC sampler for each new summary. And that is too expensive. We can't afford to do it. Okay. So the other big area of ABC that is popular is model selection. We've got competing models for the data. How do we choose between models? So the papers that assess models one at a time how do we assess the fit of a model without reference to any other models? So Ollie Ratman et al. 2009 did something like that. But often we want to compare models, so that means Bayes factors if you're a Bayesian. Okay. So the Bayes factor, if you don't know, is just the marginal density of the data once you've integrated out the parameters. So ABC gives you a very natural estimator of the acceptance of this marginal likelihood. If you add up all the kernel terms, all the acceptance kernel terms, this sum approximates the marginal probability of the data. So if these are just zeros or ones, depending on whether we rejected or accepted, this is the acceptance rate. So the acceptance rate from the basic ABC gives you the probability of the data under your model. Okay. So we could do this for each model, calculate the marginal estimate for each one, and estimate the Bayes factors. So there's sequential ways of doing this and so on that are popular. But again, there needs to be a warning here. So there's a bit of a row about this over the past few years in statistics. What Christian Robert and others showed is that you have to be very careful about what summaries you're using. So suppose you're using some summary S. So we are okay if we view our answer as conditional upon S. If we're saying, we're ignoring the full data D, we're just saying, what's the best model given that we're trying to predict the summary S? Then doing this Bayes factor ABC works very well in that our ABC estimator tends to the true Bayes factor as epsilon x modeling goes to infinity. What Robert showed was that if you are viewing this as an approximation for the Bayes factor based on the full data, that it isn't going to work. Okay? That in general, even if you have a sufficient statistic, that the Bayes factor based on the sufficient statistic isn't the same as the Bayes factor based on the full data. Okay? So even if S is sufficient for theta in model 1 and S is sufficient for theta in model 2, it doesn't mean that S is sufficient for the choice of model and theta. Yeah, which is really surprising, I think. You'd expect that if S was a sufficient statistic, this Bayes factor would equal this Bayes factor, and it doesn't. So if you're going to do model selection using summaries and ABC, if you view your answer as conditional upon the summary, you're doing okay. Yes, sir.
Is there a counterexample of that?
A counterexample. Well, if you think about how we define sufficiency, so the factorization theorem for sufficiency, I don't have a blackboard, that says that if S is sufficient, we can factorize the likelihood in terms of a term that doesn't depend upon theta and a term that has theta in on the summary. Okay? The term that doesn't have theta in is different in this case to this case. Okay, so we get this extra term out here from the factorization theory, basically. So it is really surprising, I agree. Caught people out. I don't view it as a big problem. You just have to refer to your answer as a different thing. It's the conditional on your summary. Okay. So just one slide on the choice of metrics. That's the end of the choice of summary bit. So there's papers on automatic summary, selection of summaries for model selection. So very much like the Fernhead and Prangle paper. There's another Prangle, Fernhead and other authors paper from 2013 for choosing summaries that don't have this problem. Okay, so not much work has been done on the choice of metric. So we're using uniform ABC. How do we choose a good metric? And I don't really have much to say apart from that it's important. Okay? I can construct counterexamples where it matters if you use a bad metric. I don't particularly have any advice about generically good metrics. I'm not sure anything's been written. But as an example of a bad metric, consider a very simple thing where we've just got linear dynamics as well. So not linear. We've got a dynamical system, so some state evolving in time with some Gaussian noise. And these could be linear. An observation of X with some noise, so just like a filtering model. And we want to estimate these variances. So a very common kind of problem. You might think that a good choice of summary would just be the L2 metric, L2 norm, yeah? Or the sum of squares. But turns out, well, I'll show you the figure in a minute. That's not come out very well, has it? So this is a plot of sigma versus tau, and it's a contour plot of this metric for varying sigma and tau. And basically, what you find is the minimum lies upon a line, so you can't tell anything about what the best value of the parameter is. You cannot determine it. Because it's a variance parameters, and you can't learn variance parameters from measures of scale very easily. Yeah? If we use a proper scoring rule as the metric, so if you don't know about proper scoring rules, they're scoring rules that mean you are penalized if you don't tell the truth. Okay? So the CRPS, continuously ranked probability score, is a particularly useful scoring rule. It doesn't really matter on the details, but if you use a scoring rule, they're designed so that you're penalized if you don't tell the truth. So in other words, if you pretend you're more confident than you are. So this is an improper scoring rule. So you are not penalized if you take sigma and tau too large or too small. Okay? All that matters is the ratio of sigma and tau, because there's no penalty for variance. If you use a proper scoring rule that's got a variance term in, you find the contour plot gets in the right area. So the true value is 1, 1 in here, so they can determine. So I don't have advice for what the best score is in here, the best metric. I'm not aware particularly of too much work on what we should be doing, but the choice does matter. Okay, so I'm going to leave time for questions. So what I thought I'd do with Neil's suggestion was talk a little bit about, well, 2 slides of my rejected NIPS submission. He said this is a done thing in tutorials to say, yeah, this is what you could have heard. So this is an unfinished work. It was rejected for perfectly sound reasons. But I think it's a machine learning type of problem. How can we get quicker inference using kind of models of likelihood, so maybe Gaussian process models. So the key thing about Monte Carlo algorithms is that they're guaranteed to work if you do it for long enough. If you simulate for long enough, they're going to work. But they're naive. They don't learn from previous simulations. And they don't exploit things like continuity of the likelihood function. So if instead we start to, if we move away from Monte Carlo, and then we can build in models that know that our likelihood function is continuous, for example. Okay? And we could use space filling designs and so on to try and fill space efficiently. Okay. So the key idea is that at any given value of theta, we can estimate the likelihood using kind of our GABC framework, or acceptance rate if you want, in the uniform framework. Okay? So we just run the simulator multiple times at theta, get different x's, and add up these different acceptance kernels. And that gives us an estimate, a noisy estimate, of the likelihood. And for most problems, we believe that this is going to be a smooth, continuous function of theta. There might be areas where it's discontinuous, or areas where it's less smooth. But if in general it's just chaotic, we're not going to be able to do inference with Monte Carlo anyway. Okay, it's going to be too difficult. So the idea is to try and model L of theta as a function of theta and use this in place of the posterior. Okay, so I'll just show you the pictures. So what we do, we start off by just filling space. So I've got 3 parameters here, so I just put down a bunch of points, and at each point I estimate the likelihood. So we've got a noisy estimate of the likelihood, then we just fit a model. So this is of the log, negative log likelihood here, which is why it's upside down. Okay. But the red line is basically our fit, the black line is some estimate. It's the truth, sorry. And this is just a slice through the parameter space. Now this is going to be a pretty poor model. So what we do, we reject bits of space. We can say, well, over here and over here, the log negative likelihood is too large, so we just say this is definitely implausible, let's throw it out. Put more design points in, do it again. Okay? Fit a new model, rule out more bits of space, and so on. So by doing this, we can very quickly rule out large amounts of space. So after kind of 3 waves, you rule out 95% of the parameter space here. And it doesn't look it when you project it down onto a low dimensional, but that's essentially what's happening. Fit our model, so we've got a much more accurate model of the likelihood now in the bit of the space that matters. There's something funny going on over here. This might be noise from the estimate. Okay. But we've got a model that's workable, and we can find the posterior given this estimate of the likelihood. So this is just repeating someone else's analysis for the Ricker model. So the green line here is the Gaussian process posterior from the model. The black line is from this a version of ABC, so that's not exact either, and it's got MCMC problems associated, and we get pretty similar answers. The key difference is the number of simulations we've needed. The Gaussian process approach kind of needed only 1% of the number of simulations of the ABC method. So the only point for saying this is that I think we're going to need these kind of methods if we want to do inference in more complex models. If we've got models that take a second to run rather than 1,000th of a second or a minute to run, we're not going to be able to do the brute force emulation necessary. And I think this kind of modeling that the kind of modeling that machine learning people are very good at, and the kind of thing where I think a good contribution could be made by people who know how to build these models, non-parametric models like Gaussian processes. Okay, so just to conclude from everything, we have time for questions. So ABC allows us to do inference in models for which it would otherwise be impossible, but it's definitely not a silver bullet. Okay? If you can do anything other than ABC, you probably should. If you can do MCMC or doubly intractable MCMC or whatever it is, that's probably going to work much better than an ABC approach because the simulation kills you. But a lot of the time, it's all we can do. So the challenge really is to develop more efficient methods to allow inference in more expensive models. And the area of improvement, again, I'm not a machine learning person. I don't really know what the key areas are. But these feel like areas that machine learners should know something a lot about. So how do we choose good summaries and what good dimension reduction things are there? How do we do better the regression adjustments, improve models here? The neural networks are used at the moment. I'm not sure what else we were doing. Okay. How do we learn a good choice of kernel or a good metric? How do we know what the right choice is here? How do we make things quicker by this kind of likelihood method? Finally, a point from a review paper by Marion and Christian Robert was that variational methods haven't been looked at all in the ABC context yet. And what do they have to offer? In statistics, we don't tend to look at them that often. What could be done? Okay, so just finally, I'll put these slides with references on our website. But other than that, thank you for listening.
All right, so we have 10 minutes for questions. All right, start with you.
So theta often involves, theta involves dependent random variables. True. The parameter vector theta on the other side of Bayes' rule often involves dependent variables.
Yes, it could do, yes.
So how can, you mentioned earlier in the lecture but never really came back to it, how can any of these methods possibly run embarrassingly parallel with dependency in the right-hand side and the left-hand side?
I'm not sure I've entirely understood your question, but you're just going to run a different...
It might be in the sequential aspect of it.
So the sequential approaches aren't embarrassingly parallelizable, okay, because they need to talk back to each other.
That would be the sequential.
Yeah. So the sequential bit isn't easily parallelizable, and the same with MCMC. You have to think a bit harder. It's the rejection that, which again is still probably the workhorse method here, that can just be farmed out to multiple cores.
But just back to the fundamental Bayes rule. I don't believe it's parallelizable. It's embarrassingly parallelizable. I mean, unless they're all independent. If theta is composed of independent random variables, then yes, it naturally runs embarrassingly parallel. But with that's interprocess communication. As soon as you have dependencies in the distribution, coupling between the random variables, you're dead.
I think I'm missing something in your question. That the all you're doing on the different cores is a given realization of theta running this simulator. And so what you're aiming to get are independent draws from the posterior. Okay? So if you've imputed everything, so theta contains all your random variables, you can do that, I think, unless I'm missing.
Let's just so we can get to, I see a lot of people with interest to ask questions, so yeah, this sounds like technical, so maybe take it offline.
Can you please go over the slide that you skipped, if it's still possible?
Which one?
The Gaussian process slide.
Gaussian process slide?
This, so which one, sorry? Say stop.
The equations for the Gaussian process technique for ABC.
Oh, right, okay, yeah, sure. This one, or this?
The next one.
Okay. So what we're doing is we're modeling, for example, the log likelihood, where we've estimated the log likelihood at different points. And I'm going to fit a Gaussian process as a function of theta through the different estimated points. In practice, the Gaussian process can't work over so many scales. So I have to do things like a log to begin with, and then I have to do the log of the negative log, and I have to do this kind of wave to cut out bits of space of them plausible and just assume they're going to be zero density in the posterior. But we can do things like this, and it takes a bit of tuning, but it does work in problems with a bit of work.
More questions?
You mentioned early on about the kernel interpretation of ABC. So what kind of methods are there to, say, optimize the bandwidth for these things, or in other words, control epsilon? Yeah, so I mean, the answer you always want is that you want to take epsilon as small as possible. What people have shown is that they've shown results that there's an optimal choice for epsilon in terms of the amount of computation you have. Let me get this right. So I cut a slide out on this. So depending on the variance of your simulator, you can take epsilon small enough that it's not going to make any difference. So that paper, sorry, there's no power to the charger, so my laptop keeps cut out. The paper by, I won't go all the way back. The paper by Blum, 2010, has a couple of theorems in about how the error scales with the bandwidth parameter. And Fernhead and Prangle, 2012, has it in as well. Okay. So there are people who have done that calculation. Okay.
Another question?
Hey, so I'm wondering whether ABC has been used or might be a good match for, say, a scenario where you are able to approximate the value of your likelihood function. Say if you wanted to do like approximate matrix multiplication or something like that, then you could think of it as like you're sampling, each evaluation of that is like sampling from a distribution that's like centered on the actual value of the likelihood function. Would this be a good match for that, or would you more want to just do something more traditional and just say, like, you know, you're not expecting your likelihood to always increase or something like that?
I mean, it's not directly an ABC approach, because ABC is with the simulation. But I'm sure there are ABC approaches that you could adapt to those kind of things. Perhaps more, if your estimator of the likelihood is unbiased, the pseudo-marginal methods will work in those kind of situations. If you know, if you have an unbiased estimator of the likelihood, then the Andrew 2007-8 et al. Paper, or the Roberts and Andrew paper, tells you, you know, what you can do in that kind of case.
Cool. Thank you.
Any more questions? I have a quick question, which is, you're given a simulator, that means you have code, and the code can tell you a lot about the distribution from which it's sampling. Do any of the ABC techniques take advantage of that?
So you mean because you've got a black box that you can open?
Yeah, exactly.
They don't, no.
No, okay.
I mean, that kind of, the point is that they don't. But
So there are situations which I haven't talked about where part of your likelihood might be tractable and part intractable, and then you can split the inference up. So do the ABC for the intractable bits and a likelihood technique for the tractable bits. But no, I don't know of anything particularly that opens the box and does inference.
Any last minute questions? If not, let's thank Richard.